All right, let's just jump right into one of the biggest, most mind-bending questions in all of science. Here's the thing. According to our best understanding of the Big Bang, everything you see, the stars, the planets, this world, you, me, we shouldn't exist at all. It's like we're living at a cosmic crime scene, and our very existence is the one clue that makes no sense.
So that really is the question, isn't it? Why is there something instead of nothing? The Big Bang should have been this perfectly balanced event, creating matter and its perfect mirror image, antimatter, in exactly equal amounts. And if that had happened, they would have all just canceled each other out, leaving behind a universe filled with nothing but light, pure energy. And yet, here we are.
You know, matter and antimatter are like identical twins with just one key difference. They have the exact same mass, the same weight, but they have the opposite electrical charge. So you have a positive proton in matter, and you get a negative antiproton in antimatter, a negative electron and a positive positron. It's a perfect mirror image opposition. And that opposite charge leads to a pretty dramatic finale. When a particle of matter bumps into its antimatter counterpart, they don't just bounce off each other. Nope. They completely annihilate. They vanish, converting all of their mass into a brilliant flash of pure energy. Poof! A total cancellation. And that brings us to the real heart of the mystery, this incredible cosmic imbalance. Because if the Big Bang was perfectly symmetrical, that mutual annihilation would have been the end of the story. But something went wrong. Or maybe, for us, something went perfectly right. There was a tiny, tiny glitch in the system right at the dawn of time. The leading idea is this. For every 1 billion antimatter particles created in that initial fireball, the universe somehow cooked up 1,000,000,001 particles of matter. Just one extra. So after all the pairs met up and annihilated each other, that single, lonely particle in a billion was left over. And that tiny cosmic rounding error, that's what went on to form every single thing in our universe. So how do we even start to investigate this? Well, we can thank the brilliant physicist Andrei Sakharov. Way back in 1967, he basically laid out the rules of the crime scene. He came up with 3 essential conditions that had to be met in the early universe for this imbalance to happen. Think of them as the 3 fundamental rules of physics that had to be broken for us to exist.
The official name for this whole process is baryogenesis. Now, baryon is just the scientific family name for particles like protons and neutrons, the basic building blocks of atoms. So baryogenesis is really just the story of how, in that chaotic first moment, the universe managed to make more of these building blocks than their anti-building blocks.
And here are Sakharov's 3 conditions. First, you need something called baryon number violation. It sounds complicated, but it just means you need a way to create matter out of thin air, without also creating antimatter. Second, the laws of physics themselves have to be a little biased. They can't treat matter and antimatter exactly the same. We call this CP symmetry violation. And third, all of this had to happen when the universe was wildly out of thermal equilibrium. It needed to be changing and cooling down so fast that the imbalance got locked in. Let's zoom in on that second condition, CP violation, because this is our first big clue. It's like finding a fingerprint at the crime scene. It tells us that the universe, at its most fundamental level, isn't perfectly fair. It plays favorites between matter and antimatter. So what is CP violation? Well, imagine you look in a mirror. Your reflection is a perfect flipped version of you. Physics should be like that too. An antimatter process should be a perfect mirror image of a matter process. But CP violation means that it's not. It's like looking into a funhouse mirror. The universe's mirror is just a little bit cracked. And here's the wild part. We've actually seen this. It's real. Experiments at places like CERN have confirmed that some particles do decay a little differently than their antimatter twins. So we found the fingerprint. But there's a huge problem. The amount of this rule breaking that we've actually measured, it's tiny. It's way, way too small to explain that 1 in a billion surplus that created everything. Our current theory just doesn't have an explanation for a crime this big. And that's where things get really exciting, because it means we have to look for new physics beyond what we currently know. One of the top suspects in this whole cosmic case is a theory called leptogenesis. The idea here is that maybe the imbalance didn't start with heavy particles, but with very light ones. Leptogenesis flips the script. It suggests that the first lopsidedness wasn't in baryons, but in leptons, the family that includes electrons and those ghostly little particles called neutrinos.
So the theory goes, the universe first made more leptons than antileptons, and then a little later, some other process converted that initial imbalance over to the baryons, giving us the universe we see today. So how would that work? Well, the theory imagines there were some really, really heavy, undiscovered types of neutrinos in the very early universe. As these heavy neutrinos decayed, they did so unevenly, producing slightly more leptons than antileptons. Then, a known high-energy process took that surplus of light particles and basically transformed it into the surplus of heavy particles, the protons and neutrons that make up you and me. Now, the reason so many physicists love this idea is because it's so elegant. It could potentially solve two of the biggest puzzles in physics with one single idea. Not only could it explain the matter-antimatter mystery, but it could also explain why neutrinos have mass at all, which is something our current standard model can do. Two birds, one stone.
But hang on, before we go all in on rewriting physics, we have to consider another possibility. What if the antimatter didn't vanish? What if the universe is actually perfectly balanced and all that missing antimatter is just hiding somewhere? It's a really cool thought, right? Could there be entire galaxies, maybe even whole galaxy clusters made of antimatter, just floating around in some other part of the universe? I mean, from way out here, a star made of antimatter would look exactly like a regular star. Yeah, there's a big, big problem with that idea. If you had these huge regions of matter and antimatter, they would have to have a border somewhere. And at that boundary, matter and antimatter would constantly be running into each other, creating a massive continuous fireworks display of high-energy gamma rays from all that annihilation. And here's the observational reality check. Astronomers have looked. They have scanned the entire sky with gamma-ray telescopes, searching for exactly that signature, that background glow of annihilation. And the result? Nothing. The universe is incredibly quiet in that regard. And that tells us, pretty conclusively, that our universe is overwhelmingly made of matter. The antimatter really is missing. So that brings us right back to square one. The mystery is real, the antimatter is gone, and our current rulebook, the standard model of physics, just doesn't have the answer. The solution has to be hiding in physics we haven't discovered yet. The case is still very much open. This really shows you the cutting edge of physics. The answer could be hiding almost anywhere. It could be in brand new particles we've never seen, maybe like those heavy neutrinos. It could be new forces of nature we haven't detected. It could be that the universe has symmetries that are far stranger than we imagined. Or the answer might even lie in physics from before the Big Bang itself. And I want to be really clear about this. This isn't just about cleaning up a minor detail. Finding the answer to this question won't just fill in a blank. It will completely revolutionize our understanding of reality, of the fundamental laws of nature, and our own cosmic origin story. So why is there something rather than nothing? We're here because of a tiny, lucky flaw in the fabric of the universe, right at the very beginning. We don't have the full answer yet, but every experiment, every new idea gets us one step closer to solving what might be the most profound mystery of all, the reason we exist.